Hello everyone, welcome back to the tutorial on PyTorch. Previously we had looked at what were some basic components of PyTorch like tensors and some other functionalities associated with it. In this tutorial we will look at some of the fundamental workflows involved in PyTorch, some components that are common across any PyTorch neural network training regimen. Right. So let's dig in. So these are some of the components that we will try to look at today. One thing is how do you get data ready before you can feed into a model? How do you define a model, build a model, and followed by how do you fit the defined model to your training data? And how do you take the trained model to make predictions or evaluating? And how do you save and load a trained model? Awesome. So So this is where we are creating some dummy data where we are trying to we are trying to define some x's and y's. So x and y are defined here. And we will show how we can split the data into train and test. So just a quick recap, the reason for splitting your data into train and test split is because once you the train split will be used for training the data and test split will be used for evaluating the model. These sets are different because a true test of model's performance is on unseen data. If you use the same data for both training and testing, the chances are that if the model has figured out a way to memorize the data, it performs extremely well on that training data, but beyond that, on new unseen data, it will underperform. So that's why usually one of the first steps that you take after defining your data is to split them into train and test. And train is used for training the data, and test is where you produce the final performance measures. So this is the data that we are trying to model, right? It's a simple linear regression data where there is one x and there is one y, and till here the blue dots represent the training data and the green dot represent the test data. So let's see how do you define a model. So this is a typical class definition of any of any model. So here we are defining a linear regression model. One thing that you should probably note here is that it inherits from nn.module. So nn.module is a submodule in PyTorch, and many of these components, many of these layers are predefined in torch.nn, and nn.module is the superclass from which any neural network or any neural model will inherit in PyTorch. Right, so any class definition is followed by the init function, where you define the essential components of that network, like what are the weights, what are the layers, what are the parameters associated. And there is another component called forward, another method called forward associated with the PyTorch neural net class, and this is where you prototype how does a forward propagation happen. So let's assume that there is an input sample fed into the network. How does it pass through the network, right? So just a quick recap, any neural network definition in PyTorch has two components: init, where you define the network parameters, and there is another function called forward, where you are defining or prototyping how does the forward propagation happen in a neural network. So there are again some, like we were looking at torch.nn, like here we were inheriting from nn.module, right? Torch.nn.module. Similarly, there are other components in PyTorch which are equally important, or one should know before you get coding in it. So one thing that we'll probably see down in the code is that torch.optim contains many of these optimizers, which optimization algorithms pre-implemented, which you can use to tune your network or train your network. Right. So this is just a visual representation of what we have been just discussing. Init is where you're defining your model parameters, and forward is where you're defining how does the forward propagation happen in a model. One more parameter, again, this might be familiar or recognizable from when we were talking about tensors in the previous tutorial. This requires grad is equal to true will make that this parameter is trainable, as opposed to you can also, if you put this to false, this parameter would be frozen. It will not be trained as part of the network's training process. And nn dot parameter is basically a way to initialize your model parameters, and these are not hard coded values, and it tells basically the model that this is a parameter that keeps on updating or can be updated. Right. So since there is a lot of randomness involved in a initialization of a network, like when you start out with random initialization of the network, the weights would be randomly initialized. They would neither be zeros or ones, but they would, let's say, sample from a normal distribution or any other distribution. So since there is randomness when you're initializing a network, it is logical that when you run the same experiment twice, you might not get exactly the same results, right? So in this process, to bring in some determinism to this random process, you use a seed. This is a syntax for defining that seed. If the same code is run in, let's say, in the second time using the same seed, you will get the same results. Or let's say if you run this code in another system using the same seed, it should give you the same results. So previously we had defined the class linear regression, and this is just creating an instance of that particular class. And model dot parameters will tell you what are the parameters associated with the network. So if you look above, we had created two parameters, a weight and a bias, right? And when we print them, we see that there is a tensor. There are two weights, a parameter containing this tensor whose required grad is equal to true, and there is a second parameter. Another way of assessing the model weights could be model.state underscore dictionary, state dict. So what this does is that it gives you an ordered dictionary of a key associated with whatever the tensor was there in that model. So if you were to just take a model as is and just make predictions out of that model, you don't want to train it, then this is the way that you can do. So torch.inference mode tells PyTorch that you are not training the network, you are just putting it in inference, so you are not updating any weights. So previously in the previous cells, what we had done was we had initialized, we had defined a class called linear regression, and then we initialize a model from that class. And we had created some dummy data as well, with a simple y and x and a linear data, some part of which was split into train and some part was split into test. So here we have made some preliminary predictions. Again, mind that this model was just randomly initialized. There is no training. We are just randomly initialized a model, and we are using that model to make some predictions here. So this is y-preds. That is the predictions, and you can look at those predictions like this, right? So if you plot it on the same plot where we had visualized our data, this was the training set, the blue part, this was the test part, and we are making some predictions on the test part, right? So these red dots tell you the predictions made by the initialized model without any training. So this gives you a sense of how far the randomly initialized untrained model is from the ground, from the actual test data. Right. So which is expected, right? So if you have initialized a model and you have not trained anything and you're just making predictions, there is no expectation of that random initialized model that it will be close to the test data, or it will perform really well, right? So let's look into how we can train the model, right? So when we had randomly initialized the model and made some initial predictions, you can see that these predictions are quite far off from the actual values, right? So here in this very simple toy example where you have a simple one-dimensional input, and the y is a linear dependence on it, it's very easy for you to visualize the difference between the actual value, actual goal truth, and the predicted model's predictions, right? So this is one way for you to quantify how far off our model's predictions from the actual ground truths, right? So by comparing the distance, you can say that, okay, you can quantify it into some number which indicates how far off or how close model predictions are to to the actual labels. And in case of a regression problem, you can use MAE, mean absolute error, and this would quantify the amount of it would quantify the distance between the model's predictions and the actual labels. And there could be other functions also to compute these distances. For example, in regression, it could be a mean square error or a root mean square error. Right. So this is what we would call the loss function, or output of the loss function would be this, which is essentially telling you how far are models predictions from the ground truth, right? That it goes by various names, like criterion, loss function, cost function, objective, and all this. But the essential idea is that this loss is essentially calculating the difference between model predictions and actual labels. So we add another component to the whole process where we create a loss function which is going to compute this distance between between the predictions and the actual labels. Now that the loss has been computed, if you remember from our previous tutorial, we can use gradient descent or variations of gradient descents to tune our network. Right. So now that the loss has been calculated and you have computed how much is each parameter contributing to a loss, you can adjust the network parameters based on that particular loss. Right. So who's doing that job? Who's doing this? Now that you have done the forward pass, you have computed loss. You know how much you have done a back propagation, and you have understood how much has each weight contributed to the final loss. Now you have to adjust the network parameters, right? Depending on how much they had contributed, in which direction they had contributed. Now that is what is being done by the optimizer. So torch.optim contains many optimizers pre-implemented. We are using one of them, which is called SGD, stochastic gradient descent. There are other optimizers as well. You can refer to torch.optim's documentation to understand what they are. So for any optimizers, you pass on two arguments. One is the parameters that are to be adjusted. So here you just pass out all the parameters associated with the model, and also learning rate. Right. Learning rate, again, a recall from the previous tutorial. Learning rate defines how much you are essentially weighing the gradient. A gradient is, let's say, encapsulating what was that weight's contribution to the final model's loss, and based on that gradient, you are going to adjust the network weight, but you are adding a small parameter called learning rate to basically weigh up or weigh down. Right. So these are not the only parameters. These are also sometimes depend on the actual optimizer that you are using. So here you are using SGD, and these are two parameters associated with it. There would be others as well, which will assume some default values if you do not explicitly define them or assign them some values. Depending on different optimizers, let's say if you are using an optimizer called Adam, then you can possibly assign few more variables or define few more variables to make the model learn as you would want it to learn, right? All right. So we come to the training loop, right? Just a quick recap. What we have defined is, so far we have defined a neural network. We had instantiated that neural network into some variable, and we had done we had defined some data, and we had visualized some data, made predictions with that base model without any training, and understood how you can quantify the loss between the model's predictions and the actual labels. After that, we looked at how do you define a loss function, and we also looked at how do you define a optimizer which will adjust your network weights. Now comes the central part of this neural network training regimen, where you would iterate over your training data, and you will adjust your network, or you train your network, right? So this is the essential flow of any neural network training regimen, right? You start with the for loop for your epochs. Epochs are essentially how many times is the model going to look at a particular training data, right? It might not be sufficient that you pass your training data once through the network and it learns everything. Sometimes it's of value to pass on the same training data through the network multiple times, and that is what epochs are, right? And model.train is essentially telling the model that you are in training mode, or setting the model in a training mode. That means that it would now be accumulating gradients, and uh, it would be adjusted based on whatever model predictions are made, and backward propagation. So first step that you take here is that you make predictions of the model. You pass the trained data and take the predictions. Now, having gotten the predictions, you compute the loss to understand how far off or how close are model's predictions to the actual truth. After that, once you have calculated the loss, you say that you call this function for zeroing out all the gradients. So optimizer.zero grad, zero underscore grad, this function call, what it will do is that it will zero out all the gradients in the network. Otherwise they keep on accumulating. So one of the downside of accumulating gradients is that it will boost up the memory usage, and also the next adjustment to network weights will not just be conditioned on the current data, but what other losses or other gradients that were accumulated in previous training steps as well, right? So this is a way, this is the syntax for ensuring that currently all the gradients are zeroed out. And the next step is basically to, based on whatever loss you have calculated, you do a backward propagation. So what backprop will do is that it will compute what were the gradients associated with each neural network weight based on whatever loss was there, right? Now that you have computed the gradients, the logical next step is to adjust those network weights based on their gradients, right? That's what this optimizer.step would do, right? So so the step number 4 is calculating the gradients using loss.backward, and this is again a function of whatever loss or the quantity of loss that was computed based on model's forward pass. And once you have calculated the gradients, you use those gradients to adjust those weights. So this is how a network training would proceed. All right. So previously we had looked at what was the training loop of a neural network. Similarly, if you were to do a testing loop, what you would do is that you can write essentially the same for loop, and at the end of the training loop you can add small evaluation loop or test loop, which would give you a sense of how the model is performing based on how the training is progressing, right? So the training loop or the testing loop would contain these essential components, where if you remember in the model train, you had while training the model, you had set the model in a train mode, so model.train. While evaluating, you say model.eval to put the model in evaluation mode. And you can pass on the same data and make a forward pass and take the predictions, right? And you can also, based on the model predictions, you can compute the loss, right? So here again, based on whatever the model predictions are, you can again compute any other performance metric that you might want to look while doing evaluation. If you want to, if this was a classification example, you could have looked at a metric like accuracy or F1, right? So one thing to note here is that this eval loop will, as opposed to the training loop, will not have anything about backward propagation or optimization, right? So this will stop at just the loss calculation, so that you can look at while the network is training, how is the how is model's performance on, let's say, unseen data or data that is not part of training data. It could be eval split, or it could be a test split. Right. So this is where we are implementing the same idea and training our model that we had defined earlier. Right. So we are using model 0 and going ahead and training it. And this is essentially the same loop that we had looked at above. So let's carry on. So while training, you can print multiple values to understand how is the network training progressing. So here we have written at the end of every I think 10 epochs, we will print out what was the train loss and what was the test loss. So what you can observe probably from the train loss is that it is decreasing as you go epoch by epoch, right? From 312 it decreased to 0.31 decreased to 0.19, but of course as the network training progressed, the incremental decrease in the train loss was magnitude of that reduction in loss is not as much as you had seen in the first steps, which is also logical. And along with the train loss, if you look at test loss as well, it is also uniformly decreasing, which is a good sign, which tells you that network is training well, and even on unseen data, it is gradually decreasing. The loss is gradually decreasing. So this is the typical training behavior that you would want. Your train loss is decreasing, as well as your test losses should also decrease. So if you can plot these losses, and I mean as a function, on x-axis you have epochs and on y-axis you have loss, and by looking at these curves you can get a sense of how the training of the network is going on, right? And you can see that your test loss is always slightly above than the train loss, because test data was not part of your training data set. It is unseen data as far as the model is concerned, and hence it will have slightly more loss as compared to the train set. Right. So once the network is trained, you can again look at the same model parameters to see whether they actually got adjusted or not. And if you go back and look at it, these weights have actually adjusted. So you started with a weight of 0.7, but after training it has become 0.57, and bias has also trained from 0.3 to 0.35. Right. So your network weights have indeed been adjusted as part of the training. Right. So using the trained model, you can make predictions again, just to see plot where you stand now, and you can see that now the model's predictions are much more closer to the actual data, right? So let's compare it with the initial predictions that you had made. The predictions that you had made with an untrained model, just a randomly initialized model, right? So these were the predictions that the model made when there was no training involved, just random predictions, randomly initialized, and predictions based on that. And you can see that they were far off. But now after you have done some training using the data, you can see that they have yeah, you can see now that the model predictions are much closer to the actual labels. Right. So for you to save a model, there are some functions that you can use. Torch.save would save the model. Torch.load would save. You can load a saved model, and load state dictionary. You can basically the same state dictionary that you were looking at above. This state dictionary, where there are keys are your model parameter names and the associated tensors. You can use that state dictionary also, and you can load it you can load that saved model as well, or that saved state dictionary as well. Right. So this is a simple syntax to do that, where you said torch.save model 0.state dictionary, and you are giving it some path where to save. For you to load a saved model, first thing that you have to do is you have to initialize the model, the linear regression model, and then you say that particular model dot load state dictionary and torch load, and then whatever the path was there. Okay? So this is how you can save a model and load a model. Now again, you can put that loaded model in eval mode and make either predictions, or you can decide to train it further. Right? So yeah, so the next piece of code is essentially all of them put together. You can look at it in your own time, but this is essentially an example of how you can define a neural network. How do you define a neural network, how do you train a neural network, and how do you evaluate, how do you plot the difference, or plot the similarities between the test data and the model's predictions. And there we had also looked at how do you save a model, load a model. So in this notebook, a quick recap, we have covered the basic components of PyTorch training methodology. What are the essential components involved in any PyTorch neural network training regimen, irrespective of what the model, small or big, are. All right. Thank you for your attention. I'll see you in the next tutorial.